Hello everyone. So today let's solve the problem 3133 minimum array and right. So let's see what the question states, Yaman. So we must build an increasing array of n positive integers, right? Whose bitwise and equals x. Whose bitwise and equals x. What we need to build here? We need to build an increasing array of n positive integers, right? Whose bitwise and equals x. So all the elements must contain every one bit of x, right? So that is in simple terms, each element of this one bitwise and x, that is equivalent to it should be equivalent to the x. So I can just represent in this way, bitwise and x equivalent to the x basically, right? So what we need to return here, we need to return the minimum possible last element, nothing but the nums of n minus 1, right? So here uh, this make shows that we have to make use of the bit manipulation itself to solve this particular problem, right? So we will be making use of the bit manipulation to solve this particular problem, right? So this is fine, I believe. Let's move on with the first example. Let's consider the same first example directly for the approach so that we can just try to implement the same thing for the second example, right? So let me show this one. Let's discuss the approach for the by considering the first example. So now we have n equals 3, x equals 4, right? So let's discuss the bit manipulation idea here, right? So every valid element that is equivalent to x plus t, right? Every valid element that is equivalent to the x plus t, where t only uses the bit positions, where x has 0, right? So why we are doing this? Because bits 1 in x must be present on all the elements, right? So we know this one, right? So this is fine. Yeah. Now let's move on with the second point. The set of valid numbers that is in the increasing order, right? So that is equals x plus, so we can just represent in this way, x plus 0 comma 1 that is placed in 0th position basically, right? That is placed in 0th position. Also 2 placed in 0 position, and then it goes on. So just give me a second here. Yep. Then we'll consider 3 that is placed in 0th position, and so on, right? So we can just write it in this way. So the nth smallest valid value is nothing but x plus this one. What do we call? F of n minus 1. F of n minus 1, where f of k writes the binary of k into the 0, this one bit positions of the x, right? So let's try to implement the same thing for the example 1, man. Let's consider this example. We have n equals 3 and x equals 4, right? So now just listen to this carefully. So when you see the implementation, most of the times implementing this one in the form of code will be easy, right? So this one will be x equals 100 to the base 2, right? So this is fine. So 0 positions, nothing but the from LSB, right? So we are considering from the LSB, least significant bit. So 0 positions from LSB are, so this one we can just write it in this way, 0, 1, 3 up to this one, 0, 1, 3 goes on actually, right? So k equals n minus 1 here. K equals n minus 1. N minus 1, n we have 3 and n minus 1 is nothing but 3 minus 1, we have got 2, right? This is fine. So now basically we are going with n equals 3, x equals 4. Uh, so 0 positions from LSB are 0, 1, 3 up to this one, k equals n minus 1, that is equivalent to 2, which in turn we get the answer 10 to the base 2, right? 10 to the base 2. Now what we will do, we will place its least significant bit or the LSB 0 at the position 0, meaning we will do nothing here. Next bit 1 at the position 1, which contributes to, right? So answer we have to go with 4 plus 2 here. Again, I'm telling why we are summing up 4 plus 2 here. We are just placing its LSB 0 at the position 0. We are doing nothing here. Next bit 1 is there, right? At the position 1, right? So this contributes the answer 2. This contributes answer 2. So total answer we have to go with this one, 4 plus 2, which is equivalent to the 6, right? So nums can be here, this one, 4, 5, and 6. 4, 5, and 6, right? 4, 5, 6. right? So the output that we got here is this one. What do we call 6? 4 plus 2 that led to 6, right? So the output that we got here is 6, which is equivalent to the output that they have given for the example one within the question. So our approach works absolutely correct here. So one more thing, this mapping, whatever we have done, this is nothing but because number of bits and it uses only bit operations, right? So overall time complexity would lead to this one. Sorry, yeah, overall time complexity is this one, mapping text because of number of bits and it uses only bit operations, right? So the answer that we got here is 6, which is equivalent to the output that they have given for the example one. So our approach works absolutely correct here in this case. Let me remove this one. Let's quickly discuss the complexities part, man. So what will be the time complexity here? We can just represent this one by big of b. So why we are going with the big of b here? So b is nothing but the number of bit positions that is scanned. That this is equivalent to big of logarithmic n plus this one, bits of x, basically bits of x, right? So this is equivalent to the logarithmic n plus bits of x, right? This is fine, which is tiny for the given constraints, right? So this we can just represent this one in the form of big of b in simple terms, right? So I'll just go with the time complexity big of b. So what will be the space complexity here? It is big of 1 because we'll be making use of only few primitive variables, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of b or big of logarithmic n plus bits of x and big of 1 respectively, right? So now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. First step here, let's do one thing. So let's go with the k. K is nothing but we have discussed this one. How many steps beyond x we need, right? So 0 equivalent to x itself. 1 will be next. Like that, it moves on. So let me initialize k here, not the x one. K equals long of this one. I can just write it on this way, n minus 1 l. So we are making use of long, right? So we have to provide L here along with the integer. And now let's make use of the result variable answer or ANS that will hold the this one resulting last element. So we'll start from the x, right? Smallest valid element that we had that we have already considered, that we have already discussed within the approach. Right. So I'll just go with a long answer variable long of this one x, nothing but base value x1 bits are fixed here. Next we'll be going with x as long for the safe shifting and masking, right? So this one will be long lx, that is equivalent to the long again x. Finally, let me do one thing. Let me initialize positions to 0, right? Let's do one thing. Let's consume all the bits of the k by placing them into the 0 bit positions of x. Let's go with a while loop. So this one while k greater than 0l, then what we will do? So if the bits position in the x is 0, we can place the next low bit of k here, right? So let's check if x has 0 at the position pvos, right? So let me go with if condition here. So this one will be lx right shift position. This is fine. Bitwise and we have to go with a 1 uh, as well as we have to go with the L because we are making use of the long here. This is fine. Yep. Mm, this one we have closed. Have closed. Yeah. Let me consider this one. One more. This one parenthesis over here. Right. Had missed the parenthesis. So this one equivalent to the 0L. Then what we need to do here, if the lowest bit of k itself is 1, then we have to set bit position pvos variable we have considered, right? Pvos in the answer. Let's write the one more if condition. So this one will be k bitwise and 1l. So this is equivalent to the 1l. This is fine. Now let me go with the answer logical or equals. So this one I can just give here 1l left shift position, right? So this is fine, man. Yep. After doing this, let's consume the lowest bit of the Okay, so we have to go with the right shift, right? Uh, right shift basically. So this is fine. K1, we're just consuming the lowest bit of the K. Finally, we have to always move to the next bit position after the this one. What consuming the lowest bit of the K, right? So we have to increment the this one position in simple terms. Pivot variable we have considered. So this one, let's go with the minimum possible nums of n minus one. So this one will be return answer. This is fine. Let me format the code once and let me hit the run button. I hope this works, man. Yeah, yep, finally. The sample test cases are getting passed here. So let me hit the submit button. You can clearly see here, all the test cases are getting passed, means the code works absolutely correct, right? For all the test cases. So I hope the solution part is completely clear along with the approach and the complexities for now. This is it. Basically, I want to tell you one more thing. So this is the end of the bit manipulation problems, right? So we are left with only two this one topics in the Leetcode. One is this one dynamic programming, and another one is graph. So we have already finished the dynamic programming this one problems, right? Solving 50 problems, this one using the dynamic programming of the code chef, right? So we considered 50 main problems, all the topics we considered. Uh, right, and we have solved 50 problems, 50 dynamic programming problems, right? So now we are solving the graph based problems in the Codeforces. Now if I solve the graph itself again, it will be this one, it will be based of type. So there also I'm solving graph. This one Codeforces problems also I'm solving graph, and the Leetcode problems also I'll be solving graph. So this doesn't make sense. So let's do one thing. So let's continue solving the graph problems. We are at the last topic basically. So we have solved around 6 to 7 problems, I think, or 8 problems maybe. So we'll be solving, as I've said, we are left with some 40 plus problems in the graph and the this thing Codeforces. So now we are left with DP as well as the graph and the this one Leetcode problems. So let's solve the DP problem so that we can learn this one parallelly, these two things, right? So one is graph and another one is DP. We have the idea, we can just solve n number of DP problems quickly in the Leetcode, right? So we can do that, and then we can just solve the graph problems that is left in the Leetcode. So I don't want to solve the graph problems in the this one Codeforces, this one CP problems as well along with the Leetcode. I don't want to solve that one graph problems itself, right, at the same time. So let's solve the graph problems from the Codeforces. Let's continue that, and in the Leetcode, let's solve some this one, whatever the DP problems that we have, right? So from tomorrow, we'll be solving the problems on the DP, right? Dynamic programming. Right? So that's what we will be doing. Leetcode problems I'm speaking of, and we'll be continuing with the graph problems that we are solving. Codeforces problems I'm speaking of, right? So these will be doing. So we are done with the this one solving bit manipulation based problems, right? So this is going to be the last problem, as I've said. So we are at the end of the this one. What do we call solving the problems on all the topics, right? We have completed most of the topics. We are left with graph and this one Codeforces problems. We are solving the problems on the graph. That is the last topic, and this one we will be solving this one. These are the last two topics. The Leetcode problems I'm speaking of, whatever we'll be solving from tomorrow. We are left with only two topics. One is dynamic programming and the graph. We are almost at the end. So we'll be finishing it off within basically 30 to 40 days, man. Everything will be finishing it off. So after solving these problems, after finishing this one, we will be left with only this one, certain algorithms, right? So we are left with some, we'll be completing this one, I believe. What do we call? What do you call that one? Mm, tree-based algorithms, right? So we'll be completing that one today or tomorrow. So from tomorrow, we'll be starting the graph-based algorithms, I believe. Whatever the algorithm playlist that we are discussing, so that will complete. Basically, tree-based algorithms will be completing it tomorrow, I believe. So we'll be starting this one, graph based algorithms from tomorrow. So we have hell lot of this one algorithms within the graph, right? Whether it may be Kruskal, whether it may be Dijkstra's algorithm, DFS, BFS, uh, yeah, this one MST, this one that includes this one all Prim's algorithm, those kind of algorithms, right? So we have a lot of algorithms within the graph that we'll be discussing from tomorrow, right? So this is fine, I believe. Now we are done with the bit manipulation problems. From tomorrow, we'll be discussing this one. What do we call DP based problems, right? So this is it for now. For now, this is it. Thanks for watching, guys.